Okay, so today, thank you for joining the open seminar of our team, non-convex learning theory team. Well, here are some important notice about this seminar. So, at first, reproduction is prohibited. And second, reproducing all or any part of the content is prohibited without the author's permission. And this seminar will be recorded and the video will be available on the Weekend AIP website later. And fourth, if you have any questions or comments, please scroll to the bottom of the page and click the Q&A tab. So you can put questions or comments in the box. Okay. Well, this is some important notice about this seminar. Yeah. So thank you for your attention. And I'm Kanamori, the team leader of this team, non-convex learning theory team. Okay, let's start the first talk. Thank you for joining the open seminar of our team. I'm Kanamori, the team leader of non-convex learning theory team. Today, we will report the research activity of our team. Okay, this is the scope of our team. In our team, we study mathematical properties of learning algorithms. There are many learning algorithms applied in practice. From the theoretical viewpoint, we investigate the reason why the algorithm works efficiently. And then we try to reveal the theoretical potential and limitation of existing method under a specific mathematical framework. So based on theoretical insight, we also develop new learning algorithms and theoretical models beyond existing ones. Furthermore, we aim to propose new problem settings inspired by outcomes from application-oriented teams in AIP or other research institutions. So this is an overview of recent study published from our team. In today's talk, I will introduce statistical inference with unnormalized models. In the big data era, we need to use large statistical models to capture complicated data structure. In such a problem, often we face the computational issue. So we developed statistical methods to deal with computationally intractable statistical models. Another research topic is density-rich estimation and its applications. The density-rich is a nonlinear structure of data. We develop an accurate and computationally efficient statistical method to capture such a complicated data structure. Third, we will introduce transfer learning. So transfer learning is one of the central research issues in modern learning theory. So we theoretically studied statistical properties of transfer learning. Furthermore, we developed a new transfer learning method using the concept of lasso. Fourth, ensemble learning is also an important paradigm in machine learning. The framework of ensemble learning, the simple learning models can be enhanced by combining simple models in clever way. So we show that not only the linear combination of simple models, but also nonlinear extension of the models is quite important to achieve high prediction accuracy. We established mathematical theory for nonlinear ensemble learning methods. As a fifth topic, well, recently we developed a clustering method using deep neural networks. Undoubtedly, deep learning is the most important topic in modern science. So we are now focusing on developing a new learning algorithm using deep neural networks. In my talk, I'll briefly introduce a topic of statistical inference with unnormalized models, density rich, and the theoretical analysis of transfer learning. And after that, each member will talk about their own research topics in this seminar. First, I briefly introduce statistical inference with unnormalized models. The problem setting is the following. Suppose we observe IID data x1 to xn from the probability distribution Q. Here, D is a D-dimensional space, and our target is to estimate the probability Q using the statistical model P theta. Here, theta is the R-dimensional model parameter. Suppose the statistical model P theta is expressed by P tilde theta over Z theta. Here, Z theta is a normalization constant defined by this integral. In many practical problems, the computation of Z theta is infeasible. So that is a challenge of this research. So we cannot directly apply the standard estimators, such as the maximum likelihood estimators. So this is an example of unnormalized models. In left figure, the statistical model is expressed by the exponential family, like this. This is a popular class in statistics, but if the sufficient statistics phi is obtained by the feature extractor of stacked autoencoder like this, then the computation of the normalization constant is not feasible. Another example is shown in this figure. The model is given as a Gaussian mixture model, but the domain of the data is not simple like this. So also, in this case, the computation of the normalization constant is generally infeasible. So though we can compute the function value of the unnormalized models. So our target is to develop computationally efficient and statistically accurate estimator for unnormalized models. As shown here, our team developed several learning methods for unnormalized models. For discrete data, we developed learning methods using squaring rules for unnormalized models. For the continuous data, we developed a new estimator. The idea is to approximate the maximum likelihood estimator only using the unnormalized model. There are many existing methods to deal with unnormalized models. Noise constructive estimator, NCE, is a popular method for that purpose. In our study in 2020, we improved the NCE and we proved some theoretical advantage of the improved estimator. And also, we studied the estimator using Fisher divergence. The Fisher divergence is a popular divergence to deal with unnormalized models. But when we employ Fisher divergence, the domain of data should satisfy some assumptions. In this study, we propose an estimator using weighted Fisher divergence that is available for data with general domains. Okay, so I'll introduce the approximation of the maximal likelihood estimator and the estimator using the Fisher divergence. So it is well known that the maximization of the likelihood function is equivalent with the Kahlberg-Leibler divergence. And in our method, we utilize the variational expression of the Kahlberg-Leibler divergence to obtain the approximate maximal likelihood estimator using unnormalized models. So the Kahlberg-Leibler divergence is the standard divergence to measure the discrepancy between two probabilities, like this. And the Kehl divergence is expressed by this variational form. Here, the maximization is taken over all function R of x such that the expectation under the probability P is equal to 1. So we can approximate this variational form by empirical mean over the training data like this. This variational form approximates the distance between true probability Q and the statistical model P theta. The constraint to the function R is expressed as the expectation under the model P theta. So here the computation of the constraint is not feasible. So we need to access the normalization constant to guarantee the function R satisfies this constraint. To avoid the computation of the normalization constant, we introduce the parametric model for the function R that automatically satisfies this constraint. For that purpose, we use a Stein operator. So here, T sub P is a Stein operator. This is a different, so here F is a differential function. And this function F is converted to other function Tp of F. Under the mild assumption, the expectation of Tp F is equal to 0 for any probability P. This property is used to express this equality constraint under the probability P theta. For the computation of the Stein operator, we do not need the normalization constant. That is a great advantage of the Stein operator. So in this research, we investigated some statistical and computational properties of the proposed estimator, such as asymptotic variance of the estimator, information criterion, and computation efficiency, and so on. This is a simple example of our method. The problem is outlier detection. As a benchmark data, we use the MNIST dataset like this. The data consists of handwritten characters, images, represented as high dimensional space. And also each data has a label from 0 to 1. At first, we trained autoencoder to extract 20-dimensional feature vector. Then statistical model P theta is defined as the exponential family with the feature vector as a sufficient statistics like this. And the model parameter is estimated from the training data, and we can detect the outlier from the data by comparing to the function value of the unnormalized model. Even if the statistical model is not normalized, one can compare the degree of anomaly of each sample in observed data. So here, this one, lower panel show the images with low densities comparing to the other images. The upper row shows the result of our method, and the lower part shows the result obtained by the noise conservative estimator. And it can be seen that the lowest ranking images by our method tend to be outlier in that digit group. The lowest ranked images by MCE looks very regular. So this experiment shows the usefulness of our method when working with complex models such as deep neural networks on a high dimensional dataset. Okay, let us consider other estimator for unnormalized models. And this is a map of Chicago. So each dot means the location where crime occurred in 2008. The Gaussian mixture model can be a candidate to capture the statistical tendency of this data. However, the computation of the normalization constant on this domain is not feasible because the domain is truncated and complicated. Furthermore, the data on the truncated domain, the estimator using the Stein operator does not work as it is. For such a truncated domain, the Monte Carlo method is available to compute the normalization constant. However, the statistical accuracy of the Monte Carlo method is not necessarily high. So we developed another estimator using unnormalized models to deal with the truncated domain. The idea is to use Fisher divergence with some appropriate weighting function. The Fisher divergence is a discrepancy measure between two distributions. A remarkable property of Fisher divergence is that we do not need the normalization constant to compute the divergence. The weighted Fisher divergence has been already applied for statistical inference. In our study, we use an appropriate weight to deal with complicated shape domain. So as a weight for Fisher divergence, we use a distance function from the point x in the domain to the domain boundary. So this is the Fisher divergence we used in our study. The standard Fisher divergence is obtained by replacing this red factor with the constant. Here, the derivative is calculated for the variable x, not the model parameter. So due to the derivative by the variable x, we can see that normalization constant vanishes. So next, we need to approximate the Fisher divergence using the training data. The expression in the definition is not suitable for empirical approximation. However, we can see that Green's theorem guarantees Fisher divergence is expressed as a form of expectation of the loss function. That is, weighted Fisher divergence is expressed as a form of M estimator. So when we use a distance function, we can remove the extra term in the Green's theorem. For the original unweighted Fisher divergence, the integration by part is used to derive the corresponding M estimator. For general domain, like this, we need to use the Green's integration formula to derive the corresponding M estimator. In our estimator, we need to compute the distance function. For some domains, this is computationally feasible. For general domains, some numerical methods have been developed to compute the distance function, so we can use this method. In order to investigate the detailed statistical properties, we derived the non-asymptotic estimation bound of the estimator. As a result, we revealed that the relationship between the weight of the Fisher divergence and the estimation accuracy. As a second topic, let me briefly introduce the study of the density rich and its application. The problem is to extract low dimension rich structure of probability density. So this red curve here is the ridge of this mountain. So if this mountain is a probability density, this red curve is called density ridge. So this is the data plot of the location of the earthquake occurred in Madrid. And this is the data plot of galaxy in universe. And this is the synthetic data. So density rich provides critical structure of probability density, and the projection of data point onto the density rich is regarded as a nonlinear extension of the principal component. The density rich provides relevant low-dimensional feature of data. Such information is important to enhance the understanding of data structure and support more sophisticated modeling. For this problem, we propose computation-efficient learning algorithms with flexible modeling using kernel method and deep neural networks. And we studied statistical properties of our method, such as the statistical consistency of the density-rich structure. Furthermore, we propose lasso-like variable selection method for the kernel method and proved its variable selection consistency. As a third topic, let me introduce the theoretical analysis of transfer learning briefly. The transfer learning is one of the main topics in modern machine learning. There are several basic problem settings. Here, let us consider the so-called self-taught learning. Though the popular problem setting is the unsupervised domain adaptation. Suppose that we have two data domains. One is called source domain and the other is a target domain. A large amount of trained data is observed from the source domain, while only a few number of samples are observed from the target domain. The goal is to train the predictor that provides accurate prediction on the target domain. In the self-taught learning, lots of unlabeled data is observed on the source domain, like this. And a few labeled data is obtained in the target domain. We expect that the unlabeled data in source domain is available to improve the prediction accuracy on the target domain. The learning procedure is the following. First, train the feature vector on the source domain, like this. Then this feature vector is used to learn the data on the target domain. Under this problem setting, we derived some theoretical risk bound as follows. So the conclusion is that if the sufficiently large number of unlabeled data is available on the source domain, so we can achieve high prediction accuracy on the target domain. So in other words, we can avoid negative transfer. And then we applied this result to investigate the theoretical property of the dictionary learning or sparse coding, because the dictionary learning is formulated as a self-taught learning. So as a result, the prediction error band of the sparse coding is obtained, and the theoretical result was confirmed by numerical experiment. So these are a part of recent research activity of our team. So details of other research topics will be presented by the following team members. First, Dr. Takanashi will talk about nonlinear ensemble method for time series data. And then Dr. Wada will present spectral embedded deep clustering. And finally, Professor Fujisawa will give a talk about transfer learning via L1 regularization. So now we are working on various research subjects in machine learning and statistics. So, okay, thank you for your attention. Let's move on to the next talk. So next talk is given by Dr. Takanashi, and after Takanashi-san's talk, we will have a short break, maybe 5-minute short break. And during a short break, Takanashi-san and I will respond to some questions from the audience. Okay, so Takanashi-san, please start your presentation.
Thanks for introducing me, Kanamori Sensei. I'm the researcher I'm Kosa Takanashi, the researcher of the AIP at the Kanamori team. Today, I will be talking about our recent work on the nonlinear ensemble method for the time series data. Let's get started with my presentation. Okay. In this study, we examine and compare the predictive properties of the class of ensemble methods. The ensemble methods and the model averaging and ensemble learning, where the multiple sources of the forecast are combined, mitigate uncertainty from the misspecification and improve the forecast inference and decision making. This study developed a novel theoretical strategy, which we call nonlinear synthesis, based on the successive process. And using this strategy, we identify two main classes of the ensemble methods, linear combination and nonlinear synthesis, and propose an implementation of the nonlinear ensemble methods, and we call which is nonlinear synthesis. And further show that this class has the properties that we identify as a source of improved predictive performance, namely an extra term in the stochastic process that acts as a shrinkage term in the error process. And finally, we prove a specific nonlinear synthesis of the Magrian proposed by the Magrian-West form has the minimaxity of the predictive distribution in the Kalaba-Kleiber divergence. Here is my table of my contents. Next, we discuss the background of the ensemble methods and propose the recently proposed framework of the Bayesian predictive synthesis. And next, we propose and develop the theoretical framework of the using a stochastic process and to evaluate predictive performance and prove that nonlinear synthesis is superior to equal or any and all linear combinations. The next, we examine minimax analysis and utilize the developed framework to prove that the specific form of the nonlinear synthesis produce exact minimax predictive distributions with respect to Kalaba-Kleiber divergence. And finally, we provide empirical evidence through the final sample investigations. Okay. We proceed and discussing the background of the ensemble methods. And here, Hj is a probability density functions, and Xj drawn from this Hj. And the simplest form of ensembles is that linear pooling. And Wj to W1 to W capital J are selected or estimated. For example, the setting Wj equals to 1 over j, we have the equal weight model averaging. And setting weights to the posterior model probabilities, we have Bayesian model averaging. The illustration is linear combinations. And if we have the two models, A1 and A2, and the shaded areas are the individual model space, this is the A1 space, this shaded space is A2. And linear line is a predictive horizon under the linear combinations. The perpendicular dot line from the data generating process indicates that the best possible prediction of each model, of each individual model, and combination of the model. In general, the combined focus distributions need not to be included in the model each individual original shaded set, model set. As a result, a method by collecting information from the multiple source expand original model space and reach outside the reach of any individuals. This expansion is the mechanism as to how some methods can improve prediction over any individuals. Okay, we have set density-based combinations, but there is one-to-one correspondence to the random variable-based combinations. The linear ensemble method is a density-based combination, like this. And the respective stochastic variable is the linear sum of the product. And xj is drawn from this density hj. And the stochastic variable of the zj is the polynomial distributions. The stochastic variable zj takes values 1 or 0 and with the weights w1 to wj on the polynomial distributions. So it is equivalent between the concerning density-based combinations and the random variable-based combinations. So here we consider the random variable-based combination method. For the developing nonlinear synthesis, we consider the random variable-based combination methods. And using these stochastic variables, xj drawn from the hj, and some nonlinear functions defined on j-dimensional Euclid space to the real line, and the construct nonlinear synthesis functions of the f of x, x1 to the xj. This is a nonlinear combination we define. And corresponding probability distributions that generate this distribution y, this random variable y, can be drawn from, can be obtained by using variable conversion theorems. Generally, is not unique. The y is drawn from some nonlinear combination of the density such that y equal f of x. She in general is not unique. Okay, the illustration, another illustration of the nonlinear synthesis. And the nonlinear synthesis curve is the violet curve. This curve, right, is the nonlinear synthesis. Is a predictive horizon under the nonlinear synthesis, which is geometrically to visit expansion of the original model set. This expansion is illustrated as this curved line, where the geometrically distributed space is closer to the DGPs. Okay? Perpendicular to the lines is more closer. And this is closer to the DGP compared to such of the individual models and the linear combination ones. This is the mechanism of the linear combinations. Linear combinations predicted gains. Okay, next we construct some nonlinear synthesis method for the time series data concerning the random variable-based methods. Our interest is in forecasting some future period y t plus k, and k is a positive value, and some period in the future. Typically, we set k equal 1 or delta t. That is the primary concerns. And predictor of the y hat t plus delta t over 1 is comprised of the multiple models denoted by the xj. The xj is drawn from the model density function hj. And then the synthesized predictive forecast under this synthesis function, f as the f of x, and the predictive value of this synthesis value is the increment of this function, df of x. Noting that this is not a simple function of the increment of the df. F is not simple function of the dx. Okay. From each model, this dxj is drawn from this each model j. However, when the x is obeying some semi-martingale process, the Edo's lemma is whole. Edo's lemma is here. Investigating this formula, the first term is the linear combination term of the dxj. And the second, while the second term is the extra term, is not the linear combination of the xj, dxj. This is the unique properties of the nonlinear synthesis. Okay, some one implementation of the synthesis function f. This is proposed by the McLean-West. They call it Bayesian predictive synthesis. They use the dynamic linear model like this, and the predicted value y hat t plus delta t equals the inner product of the xt and theta t, but weighting variable theta t obeying some random walk processes. Seemingly, this ensemble method is a linear combination, but this synthesis function is categorized as a nonlinear synthesis and can be written by the Ito's formula. And taking the synthesis function f of x equals the inner product of xt and theta t. Theta t is obeying the random walk. So the increment of this synthesis function is represented by this formula, by the Ito's lemma. Given this equation, we can see that the extra term that is distinguished and the characteristics of the Bayesian predictive synthesis from the linear combinations. This extra term is written in the discrete time form as the intercept of the regression function. Okay, next, extending. Next, expanding the ensemble method using the nonlinear function f as a simply greater expansion than that of linear combination. However, from the practical perspective, conditions for improvement is a critical importance, which we will discuss. First, consider the conditions for which the optimal nonlinear synthesis is the optimal linear combinations. In the special case where the DGPY and XJT are all strictly martingale processes. And in general, the martingale stochastic process can be orthogonally decomposed as the following. The following theorem as follows. And XYT and XT are all strictly martingales. The YT can be decomposed as the inner product of the strictly martingale T and weighting process theta t plus excess martingale ZT. The ZT is the orthogonal martingale for all XT, for all XJT, for all J. In general, martingale process can be orthogonally decomposed. And so this theorem indicates that when the martingale conditions hold, strictly martingale condition holds, a linear combination of the predictive value drawn from the model density achieves the optimal predictive value. Thus, the predictive error between the linear combination and the nonlinear synthesis is equal. So, the linear combination is sufficient for the forecast combination in the special case where the strictly martingale processes. Okay, noting that the assumption both YT and XT being strictly martingale is not a realistic assumption for the practical data analysis. as most practical data. And thus their focus almost never strictly matching error. So this is the case where the not strictly matching error case. When YT and XT is not matching error, they are semi-matching errors. So in the semi-matching error case, nonlinear synthesis is superior to linear combinations. Since both YT and XT is not strictly matching errors, the previous sentence does not applicable. Cannot be applicable. However, we can project and decompose YT orthogonality into the semi-matching error XT and excessive matching error processes. And when the YT and the SMT is the semi-matching error, and the following for Mayer-Schweitzer decomposition hold, the semi-matching error process YT is equal to extra term plus the linear products, inner product of the weighting process and the semi-matching error increment of delta XT plus excess matching errors. This excess matching error also known as the matching error component of the XJT. JT is also known to each other this DJT. This is the matching error component of XJ, and this is a this V is a predictor component that predetermined at the present time. So this extra term is an offspring fact that this linear combination cannot cover in the term. And this is a special for the semi-matching error case. Showing some toy examples. If the data generating process YT has the form of the sum of the three Brownian motions plus and we have only two models such as semi-matching error process. It is clear from these equations, except that to this rare case, linear combination component of this one cannot optimally predict of the increment of YT due to this difference of the drift term. And thus the linear combination will always be insufficient in forecasting due to this difference of the drift term. But for nonlinear ensembles, we can take extra terms. That extra term can take this role of this drift, and then the optimality can be established. Okay. Next, we examine some min-max analysis. And returning this figure, this means that ensemble horizon of the nonlinear synthesis curved towards the DGPs. And the circumstance, we know the DGP measures. Even when we do not know the DGP measure, there is a guarantee that the nonlinear synthesis horizon is curved towards the DGP, not away from the DGP. To this extent, we examine the exact min-maxity of the predictive distribution from the nonlinear synthesis implementations. As a result, in this study, it indicates that even under worst conditions, nonlinear synthesis outperforms linear combinations and ensure that the curve towards the horizon of the implementation method towards the GDP is always curved towards the GDP, even when the true DGP density is unknown. This provides theoretical justifications and the final sample circumstances. Okay, we show the min-maxity, and before showing that min-maxity, we define some Kalber-Kleiber divergence for the predictive distributions. And the predictive distribution of the Bayesian predictive synthesis is as follows. Measurement equation is some predicted value YT plus delta t equals to extra term plus the linear combinations and noise term. Noise term of when normally distributed. The likelihood function can be constructed by the normal distribution. Distribution as follows. The predicted distribution by Bayesian updating with respect to posterior of the L theta t, and integrating over the parameter theta, we get predictive distribution with respect to the prior L. So this up and Bayesian predictive synthesis and the weighting processes are updated by this manifold. So this parameter updating by this manifold method. And next, we define the transition probability of the best possible nonlinear synthesis. Under the formula-short decompositions, any three-matching process can be decomposed as the extra term plus the linear combination of the increment of the x plus excess same-matching terms. So the transition probability can be written as this form. It depends on the FS decomposition term, A, transcript A, and the theta. And so the transition probability of the best possible nonlinear synthesis given the available information when the change the synthesis function can be represented by these two parameters. We can define the KL risk as depend on this FS function parameter. And this is the best possible predictive distribution and proposing predictive distributions, integrating over the best possible predictive distributions and integrate over taking expectation of the past value of the y. So the minimax predictive distribution can be written by this form, and maximization taking over this parameter space A and theta t, the minimization taking over the proposed predictive distribution. So we now show that predictive distribution of the Bayesian predictive synthesis proposed by the Markman West is minimax. The proof is according to the equalizer rules. That is to prove the minimax, we have the following two conditions. We show the following two conditions. One is the disk constancy of the disk of the predictive distributions. If we set and proposed predictive distribution is shift invariant. The shift the true value of ft plus theta t to the ft plus theta t to alpha minus alpha to the alpha minus linear combination of the dx. And so this predictive distribution is the shift invariant. So the Carver-Greiber risk does not depend on this parameter. So the risk and this predictive distribution is a risk constant. Next, the extended base. Next, we show the extended base. The predictive distribution of the Q depend on the initial prior of L. This risk of this predictive distribution can be approximated by the proper prior sequence like this. And then, we have obtained two conditions. Then by the equalizer rules, the proposed predictive distribution is minimax predictive density with respect to Carver-Greiber divergence. This is my main theorem of this study. Okay, we provide empirical investigation and through the final sample simulation studies. The EGP we drawn from this formula. The matching process can be written by the extra term plus linear combination term and the noise term. So the extra term and weighting value following for the random walk processes. And we have only reconstruct two models, A1 and A2, is only observing the theta 1 and theta 2. They are forecasting for the YT. So all models are misspecified. Here is comparing the mean scared forecast error averaged over the 100 simulations. We find significant improvements in the favor of the Bayesian predictive synthesis, cutting down the mean scared forecast error by the least half compared to the repeated strategies. Looking at the other ensemble strategies, we find all to be roughly the same. Through the Bayesian model averaging H out at rest, followed by the equal weight, and then the model CPE. The order is consistent throughout T, and at least theoretically, and the order of consistency throughout the C, T, and okay, next solutions. Here is a risk ratio of the competing methods, and the BPS over the equal weight, and BPS over the BMA. Risk of the BPS and the risk of the BMA, and the risk of the BPS and the risk of the BPS, and all and the comparisons calculated by the loss ratio and 10 times simulation over the 10 times simulations. So all box plot can be below the one risk ratio one, the one ratio one. And finally, we compare the contrast synchronial weight from the Bayesian method, Bayesian model averaging combination strategy. The BMA weights established sequentially is so erratic. The blue line is the weight of the model 1, and the red line is the weight of the model 2. And the BMA weights estimate sequentially and with measure shift before the sample 10, sample 100, before 100 and after 250. The pattern is somewhat unusual compared to the results in empirical studies, where the BMA weights degenerate quickly to one model because the BMA has a consistent model selection consistency. However, this could be explained by the this could be explained highly dependency nature of the two agents, where the possible probability are near equals. Here is a Bayesian predictive synthesis the weight, and the intercept term has so dominant. The blue line is the model weight of the model 1, and the red line is the weight of the model 2. This non-line posterior means of the Bayesian predictive synthesis, the coefficients over the t equal 1 to the 300. And we see that the intercept is more prominent than the coefficients and the models. As the intercept takes on the role of the drift term caused by the dependency in the agent in the models, it is understandable that the intercept is large as dependencies and misspecification is quite high. This is visually confirming by the seemingly inverse proportionality between the intercept and the coefficient. So this is a conclusion of my studies. The future study, we developed some more empirical applications and the potential avenue of development in the future study. That finished my presentation. Thank you for my listening.
Okay, thanks for the presentation. Okay, so well, if you have a question to Takanashi-san's talk and my talk, then you can put a comment or questions in the box. Yeah, just click the Q&A tab. Well, okay, so let's have a 5-minute short break. And next talk, Dr. Wada's talk will start from 4 p.m. Okay, and during a short break, we can respond to the questions from the audience. So if you have a question, then please put a comment or questions in the box. Okay, so let's start the third talk of this seminar. So next talk will be given by Dr. Wada, and the title is Spectral Embedded Deep Clustering. So please start.
Hello, everyone. My name is Yuichiro Wada. I'm currently belonging to Fujitsu Laboratory and the Riken AIP Non-Convex Learning Theory team. Today's title is Spectral Embedded Deep Clustering. Okay, let's go. And today's presentation is based on the following paper. And this research is joint work with these institutions. Okay, next is an introduction. First of all, here is a summary of contributions. We propose deep learning-based clustering method. By inputting this method, by inputting unlabeled data set and the number of clusters, it returns the estimated cluster labels. Our method is based on spectral embedding. Our method can be more robust against outliers compared to other spectral embedding-based method. Our efficiency of our method is evaluated by using 5 commonly used data sets. As a background, clustering, which is part of unsupervised learning, is cheap since it requires no labeled information. When we design clustering method, usually we use some assumptions for data set. The following two is the examples of assumptions. The left side is smoothness assumptions, and the right side is manifold assumptions. In the left side, smoothness assumption means if 2 data point is close enough, the label of 2 data point is the same, but distant, then we cannot say same or not. And the right side, manifold assumption, actually these data points belong to 3-dimensional Euclidean distance space, but actually these data points lie on 2-dimensional space. Also, there are many classical clustering methods or non-deep learning method, but often such methods face difficulty to handle a large and complicated data set. Thanks to developing of deep neural network technology, now the method employing deep neural network can handle these large and complicated data set, mainly because of statistical stochastic gradient descent and the expression power of deep neural network. However, still a previous deep clustering method had some challenge or difficulty, and one of them, such method require key conditions where the method can perform well. And in this slide, I will introduce some example of key conditions. So for example, this DEC proposal 2016, first we conduct the autoencoder in order to obtain embedded feature vectors, and then conduct k-means on the embedded feature vectors. And here, and thereafter, by using the centroids obtained by k-means, conduct clustering. And here key condition is at least the obtained embedded feature vector should be somehow friendly to k-means. Otherwise, this method will fail. And the BAID is a variational autoencoder-based method. And this method requires embedded feature vectors follow Gaussian mixture model. Otherwise, this method also fails. And IMSAT is, in my opinion, one of the best methods in this field. And this method is based on mutual information maximization criterion. And mutual information maximization implicitly require the uniform cross-balance is uniform for the data set, but not always the case. And the CAT-GAN also requires some same condition with IMSAT. And the last one is the spectral net. This is a deep learning version of the spectral clustering. This method relatively require a small number of conditions. And if I send some negative things for the spectral net, then this method is not robust against very high dimensional data set, and also not robust against outliers. And note that all above method requires number of clusters and hyperparameter tuning. And also assume fundamental assumptions such as smoothness and manifold assumption. And here, our problem setting and goal. In our setting, given information is unlabeled data set xi. Here, n means number of data points, and the xi belong to d-dimensional Euclidean space. So which means this xi is already feature vectorized. And the second information is number of clusters C. And by using this information, we aim to estimate the cluster labels of xi. Now, these estimated cluster labels is defined by yi hat. And in order to handle this task, we employ this statistical model, conditional probabilistics model, and where theta means a set of trainable parameters in deep neural network. And next is a related work with our proposed method. First one is a spectral clustering. This method group d-dimensional any feature vectors represented by x into C clusters. The below is the example. Let's say n equals 7 now, and d equal 2 and C equal 2 like this. And then firstly, this method constructs a similarity graph. And in this graph, this black dot represent data point, and this red line represent edge. And on edge, similarity weight is attached. For example, if data set is, data point is close enough, then the weight is the weight will be bigger. And such the weight is now represented by this W NN matrix. And by using this W, define diagonal degree matrix D. And then by using this W and D, define graph Laplacian L like this. And thereafter solve the eigen decomposition problem with respect to this L. And then we get the representation of X, and here X dash, and the dimension of this representation is C. And thereafter conduct a simple clustering method such as k-means, where k equals C on this X dash. Then finally we get the clustering results like this. And next related work is virtual adversarial training, also known as BAT. BAT imports smoothness to a statistical model. And here statistical model is that P theta X given Y. And use some example here. Let's say now number of clusters is 3. And this xi has some confidence distribution like this. From left to right, cluster one confidence, cluster 2 confidence, and cluster 3 confidence. So obviously, this cluster 3 has the highest confidence for this xi. And inside of this epsilon sphere, we can search some most adversarial direction. And as an example, let's say this point is the adversarial point, and this distribution is kind of opposite with this distribution, which means this point, cluster 1's confidence is very confident, unlike this distribution of xi. And this but regularizer try to minimize the distance between this this one and this one by using this criterion. And in order to minimize this criterion, we firstly have to find the adversarial vector, adversarial direction defined by like this. And this RVADB can be efficiently computed by like this. Okay, next is a proposal method. As I already told, previous deep clustering method require some key conditions. However, practically such conditions are not always satisfied. And the spectral net is one of a few methods not requiring the conditions. However, spectral net itself suffers from the outliers. And now we propose a method named SEDC, which means spectral embedded deep clustering. This method also not requires such conditions, but can be robust against outliers. Our proposal method, SEDC, is composed of the following two steps. First step, estimate the cluster labels of unlabeled data points in high density region. And then in the step 2, being assisted by the estimator labels, we estimate the cluster labels of the left unlabeled data points. And for step 1, we propose SGSC, selective geodesic spectral clustering. So finally, this proposed deep clustering method SEDC equal SGSC step 1 plus step 2. And in the next slides, I talk about the mechanism of SGSC, which is step 1 of SEDC. Inside of the SGSC algorithm, first construct a k-nearest neighbor graph G for this data points. Here, these black dots mean unlabeled data point, and then define hub data points by using G. Here, hub data points, for example, defined as high degree nodes in G. So in this example, this star data point is hub data point. And then thereafter, define geodesic metric or distance, dg, on this G by using graph shortest path distance. Then conduct spectral clustering only on hub data points by using different metric. And now this is DG. And finally, we get some cluster labels. In this example, such estimated labels represented by a triangle and rectangle, like this. Also, in step 1, by using SGSC, we estimate some of labels for whole unlabeled data points, but still we have to estimate the left labels. So in order to estimate the left cluster labels, we train this model by the following criteria. And in the first term, means virtual adversarial loss, which is already introduced in this related work section. And the second one is a cross entropy loss by using a few estimated cluster labels. And the last one is conditional entropy loss. And by minimizing conditional entropy loss, the model becomes like this. For example, at some data points, confidence distribution is like this. And after minimizing this conditional entropy loss, this distribution becomes more confident. So cluster 1's confidence becomes more confident like this. And mathematically, a second and a third term is defined like this. Okay, let's go to numerical experimental part. For the experiment, we use following data set, 5 data set, and 2 from real world data set, MNIST and Reuters 10K. MNIST is a handwritten data set from 0 to 9, and the Reuters is English news data set, and the 10K means from whole Reuters data set, only 10,000 samples sampled. And for MNIST, originally this is a 2822 pixels, but this is a naively transformed to 784 dimensional feature vector. And for Reuters, the text data is transformed to 2000 dimensional feature vector by using TF-IDF technique. And for the artificial data set, we made these 3 FC 4 clusters, but a bit noisy, and TM2 means like this, but a bit noisy again, and TR3 links like this, but a bit noisy again. And the statistics of the data set is like this. And for the clustering evaluation metric, we employ clustering accuracy defined as follows, like this, where yi true label, and the yi hat is estimated cluster label, and tau is one-to-one map from this set to this set. Here is a numerical result. This is a proposal method, and for MNIST or Reuters, this is a real world data set, performs so-so, but a bit complicated and a noisy data set. Our method is performed very well. So we average perform like this. And here is a summary or comparison with other spectral-based method. Since these 3 methods employing construction of the k-nearest neighbor graph, time complexity is at least n squared, but the spectral clustering needs some again decomposition problem solving, so NQ like this. And unlike spectral net, our method is somehow robust against outliers, but some drawbacks is hyperparameter tuning is a bit messy. So finally, the conclusion. We propose a deep clustering method named SEDC. SEDC firstly conduct SGSC for estimating cluster labels of points in high density region. And thereafter, by using such estimated cluster labels, the estimates left labels of unlabeled data points. As a property of the SEDC, robust against outliers compared to other spectral-based method. And in the numerical experiment, SEDC perform better than previous method in average. for 5 commonly used data set. And here is my reference. So I finish.
Okay, thank you for the presentation. And if you have a question or comment, then please put the questions in the box of the Q&A tab. Okay, so we can move on to the last talk by the Professor Fujisawa. Now he is not attending this seminar, but he prepared a video of his talk. So let me play his video.
Hi, I'm Hironori Fujisawa of the Institute of Statistical Mathematics. The title is Transfer Learning via L1 Regularization. This is a joint work with Dr. Takada of Toshiba Corporation. So this content was accepted at New Lips, so the paper is available at this site. This is the outline of this talk. First, I will show our motivation from our experience in manufacturing industry. Next, I will propose a new method, transfer loss. Next, I will show some theoretical results, including estimation error bound. Finally, I will illustrate some numerical experiments. This is our motivation. Here, Y is a quality characteristic. X is a high dimensional feature vector. And this is a model. Beta is a parameter of interest. And beta hat is an estimate or a lasso estimate. And in manufacturing industry, the model is evaluated or updated repeatedly every week or every few days and so on. But here, we mainly focus on two steps, past and present. First, we collect the dataset, and next, using the dataset, we estimate the model. And finally, based on the estimated model, we make judgment. When the system is judged to be stable, we can continue the system. But when the system is judged to be unstable, we must check the system to find the cause. So we must stop the system for a few days. It's not good. So how to use the dataset at the model estimation step? So there are two options. So use all the dataset at the present step. This is very strong because we have we can use many observations. So this is reasonable when the system is stable, but when the environment changes, this is not reasonable. So this is another option. Use each dataset independently at every step. But even in this case, so even under a stable system, the estimate may be unstable due to insufficient sample size or multicollinearity and so on. So in this case, we must stop the system regardless of a stable system. This is a very unfortunate situation in manufacturing industry. So we want stable parameter estimate at each step in manufacturing industry in order to continue the system. We also have prior knowledge. So, for example, some parameter estimates are obtained in advance by prior reliable big data analysis, or some features are known to be uncorrelated to a response by skilled workers. So, there are a lot of prior knowledge in manufacturing industry by skilled workers. The first case is well known as a transfer learning setting. The second case is a collaboration problem of data science and skilled workers. Recently, this is very desirable. And this problem is becoming very important. So this is our idea. This is a key of our idea. So prior knowledge is used via L1 regularization, not used as it is, because the prior knowledge may be unreliable at the present. And in addition, the proposed L1 regularization can present several parameter estimates. This property is very important in manufacturing industry. Next, I will propose a new method, transfer loss. This one is very important in this talk. Beta tilde 0 is an initial value, a kind of initial value or initial estimate. These are examples. Past reliable estimate obtained from the past big data, or parameter estimate at the previous step, or sum zero estimates just from skilled workers. There are some candidates. And this is the transfer lasso. Beta hat is the estimate. This is defined as a minimizer of the loss function with an initial value. The loss function is defined like this. This is a usual squared error loss, and this is a penalty. And the penalty consists of two terms. This is a usual L1 regularization, and this is a devised L1 regularization with an initial value. So as a result, the resulting estimate is shrunk to 0 or an initial value. There are two remarks here. Xi is the difference between the parameter and the initial value, and Ri is residual by replacing the parameter beta by the initial value here. So the loss function can be re-expressed like this. So yi is replaced by Ri. So the yi is replaced by residual, and beta is replaced by Xi. So this is a kind of residual regression. And this term is the same as the previous one. And this one is replaced by Xi. So this combination is a kind of lasso based on the residuals. In addition, the proposed new penalty is applicable to many regression problems, including non-linear regression, logistic regression, and so on. And this is a penalty, so we can choose an effect of penalty. So there is a trade-off between the present and prior knowledge or past knowledge. Here, this is based on prior knowledge, and the prior knowledge can be used strongly when alpha is 0. So this term vanishes. Sorry, this term vanishes. and the prior knowledge is not used at all when alpha is 1. In this case, this vanishes. So there is a trade-off between the present and prior knowledge. And tuning parameters are adaptively selected by cross-validation based on the present data set. And these are contour plots of this regularizer with this initial value. So this is origin, and the initial value is around here. So this is a contour plot of the usual raster. So this point is important. So the estimate is shrunk to the 0. And this line are important. And in this case, the origin and this initial value point are important. And so this line and this line and this line and this line are important. So the estimates are shrunk to 0 or initial value. So to obtain optimal value, or we can use a coordinate descent algorithm like Russell. So this is the algorithm, and this is a soft threshold function like this. So this seems to be complicated, but anyway, so this value and this value are also used in the usual Russell. And this value and this value are different from the usual Russell. So this soft threshold function seems to be complicated, but this is very simple. So this and this are figure of the soft threshold function. And this function has two truncated values, 0 and b is here. So the truncated values are 0 and initial values. So this is very reasonable. Next, I will show some theoretical results. These are important assumptions in theoretical analysis. We assume that the noise is an IID sub-Gaussian sequence with a scale parameter sigma like this. And this is a definition of the general restricted eigenvalue condition. So the restricted eigenvalue condition is often used in sparse estimation. So this is a generalization of the restricted the usual restricted eigenvalue condition. So this means a kind of smallest eigenvalue is positive. And these are notations. P is a dimension of feature vector. Beta asterisk is a true parameter. Delta is the difference between the initial value and the true parameter. And S is an active set of the true parameter. Small s is the size of this set. And Vs, the vector restricted to the index set S. And this set plays an important role in the main theorem. And this type of set is often used in sparse estimation. This is the main theorem. So we assume the sub-Gaussian property and the generalized district eigenvalue condition for this set. Then we can have this estimation error bound with high probability like this. So of course, we can easily obtain the estimation error bound for Russell when alpha is 1 and delta is 0. And this is an interesting case where delta is 0. In other words, the initial value is completely the same as the true value. This is a kind of ideal situation. So in this case, the estimation error bound of tensor Russell is smaller than the estimation error bound of Russell. This is a favorable property. And this is another theorem about convergence rate. So assume the same conditions as in the main theorem. Then with high probability, we can have this convergence rate. So in this case, this is a very ideal situation. But here we want to consider a usual case. So delta is not 0. But even if delta is not 0, we can have consistency of the proposed estimator as lambda n goes to 0. But the convergence rate is lambda n here because this is not 0. So this order is slower than the usual convergence rate lambda n squared. This is the usual convergence rate for Russell. But if this alpha is set to be 1 minus lambda n, the convergence rate is recovered to be lambda n squared. So, but the constant factor of lambda n squared is this one plus this one. So the constant factor is larger than usual. But anyway, even in this case, we can have consistency of the proposed estimator. Here, let's consider a two-stage estimation. So this is the usual data set at the present. And this is a data set at the first step or at the past steps. The primes means the first step. And this is a true parameter at the first step, and so on. And here, delta asterisk is the difference between two true parameters at the present or at the past, in the past. And here, the initial value is replaced by the last estimate at the first step. So in this case, we can have this corollary using the main theorem. We can easily show this theorem. So assume the same conditions as in the main theorem and assume similar condition for the first dataset. Then with high probability, we can have this estimation bound. although this bound is also complicated. But here, suppose the same true parameters. In other words, delta asterisk 0, and assume that we have abundant source data but few target data. This means n prime is much larger than n. So this is a typical situation of transfer learning. In this case, this bound is smaller than the bound of the usual lasso. So this is a favorable property. Finally, I will illustrate some numerical experiments. So the newsgroup message data are available at the UCI database. So this data consists of messages from Usenet posts of different topics. And there is a concept-driven experiment with pre-processed data. And there are 1,500 examples and about 900 features of Boolean bag of words. The users are interested in the topics of space and baseball in the first 600 examples, while the user's interest suddenly changes to the topic of medicine in the remaining 900 examples. The purpose is to predict either the user is interested in email messages or not. This is a typical classification problem. But there is a concept-driven situation. The examples were divided into 3 batches, each containing 50 examples. And we trained models using each batch and evaluated them using the next batch. So we compared our transfer lasso with lasso all and lasso single. Lasso all is the lasso based on all the datasets, all the past datasets. And lasso single is the lasso based only on the present dataset. This is a very conservative method. And this is a classification problem. So we use a logistic loss, not squared error loss. And we can also construct a coordinate descent algorithm. And the tuning parameter was selected by tenfold cross-validation. This is the result of area under the curve. So the sudden drift happened at here. So before the sudden drift, lasso all was the base as expected. And the transfer lasso is the second, and the lasso single was the worst. When the sudden drift happened, lasso all became worst as expected. And the second is the transfer lasso. Lasso single was the best. But after the sudden drift, transfer lasso suddenly recovered the performance. And the transfer lasso was the best. Transfer single is the second, and the lasso all was the worst. And this is a solution path. So this result shows a very interesting property in manufacturing industry, for manufacturing industry. So there are about 900 lines So one line corresponds to one coefficient. So the estimated coefficient is more stable in transfer lasso around here and so on. So this is very favorable in manufacturing industry, as I mentioned. This is a summary. So we have proposed this new penalty. And various types of prior knowledge can be incorporated into this initial value. And prior knowledge can be used adaptively by cross-validation. In theoretical analysis, we can show that the transfer lasso is better than lasso under some stable environments. In addition, transfer lasso can have consistency even under unstable environment. In the numerical experiment, transfer lasso showed a better performance and presented stable parameter estimates. This is favorable in manufacturing industry. Thank you.
Well, if you have some questions, then please put your question on the box of the Q&A. Now, Professor Fujita is not attending this seminar, but when the video is uploaded to YouTube channel, we will respond to some questions to this talk or other talks as a summary column of YouTube. So thank you for understanding. And well, yeah, thank you for joining well, today's open seminar for our team. So this is all for today's seminar. And if you are interested in the research activity of our team, so please contact us anytime. Okay, and this is final announcement. Now probably you can see the schedule of the AIP Open Seminar. So yeah, this is a SQL, the schedule of the SQL Open Seminar, and please access the link for the detailed information. Yeah, there are a lot of interesting seminars. Will be presented by other team leaders or unit leaders. So, okay, so well, today, thank you very much for your attendance and for your attention. Thank you very much. So this is the end of the open seminar of our team.